Hello everyone, and welcome back to some more remote learning. In today's video, we're going to do some examples and practice problems on improper integrals. Now up to this point, we've talked about a lot of different integration strategies and techniques, and we haven't discussed the bounds very much. So let's go ahead and talk about those. But more specifically, we're going to talk about that relating to improper integrals. Now, before you get started, I highly recommend that you just get a brush up on the limits that you learned in Calc 1, because that's going to come up a lot in this worksheet. We're going to be taking the limit as x approaches infinity, and we're also going to be taking the limit as x approaches some finite number. So definitely review those before diving in. Now, what exactly makes an integral an improper integral? Well, there's two cases that we're going to be looking at. The first is that the interval we are integrating is not finite, meaning that the bounds on those integrals, the upper and lower bounds, are either positive infinity or negative infinity. And the second case we'll be looking at is that the function to be integrated, that integrand, is unbounded. And we'll discuss that more once we get into an example. But let's start by looking at a finite interval, and then we're going to change it to be an infinite integral, so you can see that difference. So let's go ahead and look at example 1. Part A. Example 1a is that finite interval. So we're going to integrate 1 over x to the fourth from 1 to 3. So x to the fourth, if it's easier to think of it, I can think of this as the integral from 1 to 3, and I'll go ahead and zoom in since I have some room, of x to the negative 4 dx. Sometimes it's easier to visualize it like this, because in order to integrate, we're going to add 1 to that exponent and then divide by it. So this is going to become adding 1 to that exponent, x to the negative 3, and then dividing by that new exponent, negative 3. And we're evaluating this from 1 to 3. Now, I'm not a big fan of exponents that are negative in my numerators, so I'm going to bump that down to my denominator. So I'll have a negative 1 over 3x cubed. And this is from 1 to 3. So our next steps for this, we plug in 3 and subtract plugging in 1. So I'm going to have negative 1 over 3 times 3 cubed minus a negative 1 over 3 times 1 cubed. Simplifying this down, negative 1 over 3 times 3 cubed, that's going to be 1 over 3 to the fourth, which is 1 over 81, and then I'm subtracting a negative, so that's adding 1/3 to that. And in order to combine this fraction, I need to find some common denominator. So between 81 and 3, I'll just change this by multiplying 3 by 3 cubed over 3 cubed. 3 times 3 cubed, we know, is indeed that 81. So we're going to have negative 1 over 81 plus 27 over 81, which gives us 26 over 81. That's our integral of 1 over x to the fourth dx from our bounds of 1 to 3. But let's take a look if now we go from 1 to infinity. Let's just picture this graph real quick, because I think this will help. If we have 1 over x to the fourth, it looks something like this. So I'll roughly sketch 1 and then 3. So you can see that this area that we found in part A was here. So the integral we're going to find in part B goes from 1 to infinity. So from 1, but I continue on all the way out towards infinity. So what exactly is that? How do we use that infinite bound? Why do you think refreshing your limits was so important? We're going to use limits. So as opposed to having this infinity, I'm going to switch it out for b, or any arbitrary variable. So I'm going to set this integral up as 1 to some variable b. But remember, it's almost like b is representing infinity, so I'm going to take the limit as b approaches infinity of the integral from 1 to b of 1 over x to the fourth dx. Well, up above, we already integrated this, so we know that that's going to be negative 1 over 3x cubed. Remember, I still am taking this limit, so I'm going to take the limit as b approaches infinity of negative 1 over 3x cubed, and my bounds go from 1 to b. Now I'm going to plug in b and subtract plugging in 1, just like I did up above. But remember, we're taking that limit as b goes to infinity, so we need to write it in each of our steps. So I'm going to have the limit as b approaches infinity of negative 1 over 3b cubed minus a negative, so plus 1 over 3 times 1 cubed is 3. And what does this equal? If we're taking the limit as b approaches infinity, this fraction, the numerator is a constant and the denominator is getting bigger and bigger and bigger. So the overall fraction is going to go towards 0. So this is essentially 0, leaving us with the positive 1/3. So 1/3 is equivalent to the integral of 1 over x to the 4th dx from 1 to infinity. So even though we integrated this from 1 to infinity, that infinite bound, we still got a finite number, which I think is pretty neat. Let's look at this other case, example 2. Again, we have that infinite bound. So we're going to set up the limit. So I'm going to plug in some variable b and take the limit as b goes to infinity of the integral of 1b x to the 6th dx. Integrating x to the 6th, remembering that we're still taking the limit, that becomes x to the 7th over 7 from 1 to b. Plugging in b and subtracting plugging in 1, we're going to take the limit as b approaches infinity of b to the 7th over 7 minus 1 over 7, because 1 to the 7th is 1, so we're just subtracting 1/7. Now, as b goes to infinity, what does b to the 7th over 7 goes towards? We have some fraction where the numerator is getting bigger and bigger, and the denominator remains a constant. That's obviously going to go towards infinity. So this limit, even though we're subtracting 1/7, is going to be infinity. So here was an example where we had an infinite bound, and we got that the overall integral diverges. Diverging meaning it goes towards infinity, whereas converging, like in example 1 part B, goes towards a finite number. And just to think about the graph of this, you can see that if I had 1 here and I continue out towards infinity, well, that's going to get bigger and bigger and bigger as we take that area under that curve, as we integrate. So even graphically, it makes sense that we get infinity. Compared to up above, when we drew that graph, that function was getting closer and closer to 0, so closer and closer to having no area between the function and the x-axis. In example 3, not only do we have infinity on one side of our integral, we have a negative infinity on the other side of our integral. But we can't take the limit as b approaches infinity and negative infinity all in the same step, so what we're going to have to do is split this integral up. And you can choose any constant that you want for that split. I'm going to choose 0 because it's an easy number to work with. So this is going to be equal to the integral of negative infinity to 0 of my function, which is 1 over x squared plus 4, plus, now I'm going to start where my upper bound ended, so that's going to be 0 for my lower bound, to infinity of that same exact function. So I didn't change the value of this integral at all, I just split it up so that I can do one limit for each. So in the first one, I'm going to choose some arbitrary variable, let it be a. So I'm going to have the limit as a approaches, I'm plugging a in for negative infinity, so as a approaches negative infinity of the integral from a to 0 of 1 over x squared plus 4 dx. And then I'm going to add that to I'm going to have another limit. And this one's going to be the limit as b goes to a positive infinity. So you can see that I'll plug b in at that upper bound. And I have my same function, integrating that with respect to x. Now it's time to integrate, plug those bounds in, and solve. So integrating 1 over x squared plus 4, this is the form 1 over x squared plus a squared, which we know from just basic integration, that's going to integrate to be an inverse trig function, inverse tangent. If we didn't remember that form, we could have also done some simple trig substitution to solve for that. But this is indeed the inverse tangent of x over a all over a, where my a in each case, since I'm using that same function, is 2. X squared plus a squared, x squared plus 2 squared. So I'm going to have the limit as a approaches negative infinity of the inverse tangent of x over 2 all over 2 from my bounds a to 0. And I'm going to add that to the limit as b approaches infinity of, same thing, inverse tangent of x over 2 all over 2 from my bounds 0 to b. Now I'm ready to plug in and simplify. Plugging in my upper bound, starting with that, is 0. I'm going to have the limit as a approaches negative infinity of, plugging in 0, I get the inverse tangent of 0 over 2, and that's all over 2, minus inverse tangent of a over 2, and that's all over 2. And I'm going to add that to the limit as b approaches infinity of upper bound minus lower bound. That's going to be inverse tangent of b over 2 all over 2 minus the inverse tangent of 0 over 2 all over 2. Now, obviously, b is only for this term, and my limit of a is only for this term. So I could have pulled those terms that I'm plugging constants into outside of my limit. I just left it inside my limit so that you can see each of those integrals, upper bound minus the lower bound. Now, like I said before, it didn't matter what constant we chose, 1, 5, 99, -3, we could have split this integral at any point. Because if you notice, the inverse tangent of 0 over 2, I don't even care what that value is because I'm able to subtract that same exact thing over here. So if we had stopped that integral at, let's say, 5, then both of those would have a 5 in that numerator within that inverse tangent function and still cancel out. So we're left with the limit as a approaches negative infinity of negative inverse tangent of a over 2 plus the limit as b approaches infinity of the inverse tangent of b over 2 over 2. So what I want to do is, I think inverse tangent, if you don't remember what the graph looks like, is kind of hard to visualize. So let me go ahead and pull that up for you now. And I'm going to type in the inverse tangent of x over 2, so you can get a feel for how this graph looks. Now let's look at that inverse tangent of x over 2 as it approaches infinity or as it approaches negative infinity. Well, as we approach infinity, we're going to go towards pi over 2, and as we approach negative infinity, we're going to go towards a negative pi over 2. Let me go ahead and graph each of those lines really quickly so you can see that indeed we're approaching that pi over 2, that purple line, and we are indeed approaching negative pi over 2, that black line. So as we approach positive infinity, we're going towards a positive pi over 2, and as x approaches negative infinity, we're going towards a negative pi over 2. So let's go back to our worksheet and fill that in. As x approaches negative infinity, remember our inverse tangent of that a over 2, so as a approaches negative infinity, we're going towards a negative pi over 2. And remember, that's subtracted. So we have negative pi over 2 all over 2. And then we're adding that to The inverse tangent of b over 2 as b approaches infinity is going to be a positive pi over 2. So we're going to be adding pi over 2 all over 2. What's that going to be equal to? Negative times negative, that's a positive. Pi over 2 is pi over 4, plus pi over 2 is another pi over 4. Pi over 4 plus pi over 4 gives us pi over 2. So our integral in this example is equivalent to pi over 2, even though both of those bounds were infinite. Let's move on to the second page. We've completed some examples with infinite intervals. Now we're going to look at integrals where the function is unbounded. So looking at A again, it looks pretty familiar, except this time we're going from 0 to 1. Let's go ahead and zoom in. What can we not plug into our function, our integrand, 1 over x to the 4th? We can't plug in a 0 because that would be undefined. If you remember from that graph, if I tried to draw my Riemann sum and draw a rectangle at 0, there's going to be no bound to how high I have to draw my rectangle. It's unbounded at 0. So that's another case of an improper integral. So what can we not plug in? We can't plug in 0. So because we can't plug 0 in, we're going to have to take the limit. So we're going to take the limit as some variable a approaches 0, but now that we're approaching a finite number, we know we can approach from both the left and the right. So in this case, because our interval is from 0 to 1, that 0 is as we approach from the right. Since that's our starting point and we're moving towards the right, we're going to look at 0 as we had approached from the right. So this is 0 from the right of a to 1, 1 over x to the 4th dx. We've already integrated 1 over x to the 4th. We know that that's going to be, let me rewrite my limit, that is negative 1 over 3x cubed, and our bounds are from a to 1. So we're going to plug in that upper bound of 1 and subtract plugging in our lower bound of a. So this is going to be the limit as a approaches 0 from the right of negative 1 over 3 times 1 cubed, which is negative 1/3, minus a negative 1 over 3a cubed. Now looking at this limit, I know that I have some finite number, negative 1/3, and I'm subtracting a negative, so that's the same as adding a positive. But think about a approaching 0 from the right. We're approaching this with positive a values, so our denominator is going to be positive, but our denominator also is getting closer and closer to 0, so the overall fraction is getting bigger and bigger. This diverges. That limit is infinity. So this integral diverges. And let's take a look in part B. I have the same integral just to make it a little bit easier on ourselves to make this worksheet go faster, but now my bounds go from negative 1 to 1. Is there anything within this interval that I cannot plug in? Well, yeah, 0 is still in that interval. I can't plug 0 into my integrand, therefore it needs to be set up as an improper integral. So like before, I'm going to split it, but I need to split it at that point where my function is undefined. So I'm going to go from negative 1 to 0. That's where my function is undefined, and I'm going to add that from 0 to 1. Now we already know what 0 to 1 is because we've done that up above. We got that diverged. So I'm not going to write this out again, but let's go ahead and set it up just for practice. So I'm going to do the limit as b approaches 0 of the integral of negative 1 to b, 1 over x to the 4th dx. I'm going to add that to the limit as a approaches 0 of a to 1, 1 over x to the 4th dx. Now looking back at my limits, I know that I'm approaching 0 from two different directions. when my interval is -1 to 0, I'm approaching 0 from the left. So I'm going to make a note of that. And when my limit is from a to 1, that would be me approaching 0 from the right. So I'm going to, again, make a note of that. Please do not forget this, because even though with 1 over x to the 4th, as we approach 0 from either side, we go towards infinity. If you think about a function like 1 over, let's say, x cubed, as we approach from the left and as we approach from the right, we're getting two separate answers. One's going to be negative infinity, while the other would be positive infinity. So it is important to distinguish when you're approaching a finite number, whether you're going from the left or from the right. Because we know it's unbounded, we're not continuous at that point, so our limit will not necessarily be equivalent. Again, I already know what this is from up above. That gave me infinity. So I'm not going to worry about necessarily going through all that work, but I'll do it for our limit involving b. So we're going to have the limit as b approaches 0 from the left of -1 over 3x cubed from -1 to b. That's going to equal the limit as b approaches 0 from the left of -1 over 3b cubed minus a negative, so plus 1 over 3 times -1 cubed. So if we think about just this limit, ignoring adding this limit because we already know that that diverges, if we look at approaching 0 from the left, b from the left is going to be negative. Negative cubed is still a negative, however that number is getting smaller and smaller, so this fraction goes towards negative infinity, but that negative out in front, it goes towards positive infinity. So I don't even care about this constant that's added or subtracted from it. So that means that this limit also diverges. So overall, infinity plus some other infinity, we're going towards infinity. This integral in part B also diverges. And lastly on this worksheet, we'll go over example 5. So example 5 is all about what happens when we need to know whether an improper integral converges or diverges, but we can't integrate it. Well, we can use a comparison test. And later on when we get into sequences and series, we're going to be using comparison tests and limit comparison tests to figure out whether a series converges or diverges. But for now, we care about whether this integral converges or diverges. And again, it's through a comparison. So looking at A, we have cosine squared of x all over x to the 4th. I don't know how to integrate that. I would try to do a half angle identity, but then use substitution wouldn't really work out because I have that x to the 4th in the denominator and so on. So I'm not able to integrate this problem. However, I can compare it to something that I can easily integrate. Cosine squared of x, that function, even the cosine function by itself, is trapped between -1 and 1. It oscillates between -1 and 1 from negative infinity to positive infinity in the x. So if I'm squaring that, I'm going to be stuck between 0 and 1. So I know that cosine squared of x is always going to be less than or equal to what's the greatest value it's going to hold. That's going to be 1. So if this was over x to the 4th, well then I'm going to write my 1 over x to the 4th as well. But wait a second, we know exactly what happens to 1 over x to the 4th when we integrate it from 1 to infinity. We did that back in example 1. If we scroll back up to example 1, from 1 to infinity, 1 over x to the 4th dx, when integrated, was some finite value. When it was a finite value, that meant that it converges. So because we have a finite value for 1 over x to the 4th, if we're integrating some function and we know that it converges, if we can show that the function we're curious about is smaller than that, that means it also has to converge. So because cosine squared x over x to the fourth is smaller than 1 over x to the fourth, and when we integrate 1 over x to the fourth, something we can integrate, we know that it goes to some finite value, it converges. Well, there we have it. We know that, I'm going to write therefore, that's what those 3 dots mean, therefore the integral from 1 to infinity of cosine squared x all over x to the fourth dx also converges. Now, we would have an issue if this went the other way. If we said that cosine squared of x over x to the fourth was always greater than or equal to something when we integrated it and we got that it converged, well, if we're bigger than something that's converging, we could converge or we could diverge. So we wouldn't know exactly what to say. But because we're less than or equal to, and the function we compare it with when integrated converges, then the original function when integrated also converges. In part B, I'm going to show you how to show that something diverges. If we're going from 2 to infinity of this function, it's kind of hard to do a u sub with this problem because we don't have the du in our numerator of this, and trig sub's not going to work out the best for us. So let's find a good function to compare it to. Remember, all I care about is knowing whether this converges or diverges. I know that 1 over the square root of x to the 1/3 minus 1, a good comparison would be 1 over, just looking at the highest power, I'm going to look at this x to the 1/3 and the square root of that x to the 1/3. So that's x to the 1/3 raised to the 1/2, which simplifying down becomes x to the 1/6. Can I integrate x to the 1/6? Yeah, I totally can. And what comparison do we have? Well, because this denominator, when I'm subtracting 1 away from that, this is always going to be smaller. So because the denominator of the fraction is smaller, that makes the overall fraction always greater than or equal to. So if I show that this converges, well, if we're greater than something that converges, we don't know what's happening necessarily. But if I show that this integral diverges, then I can also assume that the integral of my original diverges as well. So let's quickly set this up. I'm going to have the integral from 2 to infinity. Notice I did not include 1 because if 1 was in here, we would have something undefined. So we would have to split this up and this would be a lot longer of a problem. So I did 2, so we don't have to worry about having something undefined. And I'm going to integrate 1 over x to the 1/6, which 1 over x to the 1/6 might be easier to see as x to the negative 1/6 dx. But because I have this infinity as a bound, I'm going to take the limit as b approaches infinity, and I'm going to plug b as my upper limit. So this is going to equal the limit as b approaches infinity. Let's go ahead and integrate x to the negative 1/6, adding 1 to that, negative 1/6 plus 6/6, adding 1 is going to be 5/6. So this becomes x to the 5/6 over 5/6, or 6/5 x to the 5/6. As opposed to dividing by that fraction, I multiplied by that reciprocal. And I'm evaluating this from 2 to b. So this is going to be the limit as b approaches infinity of 6/5 b to the 5/6 minus 6/5 times 2 to the 5/6. Looking at this limit, as b approaches infinity, this term is going to continue to go towards infinity. 6/5 b to the 5/6 will continue towards infinity. Therefore, regardless of this constant over here that I'm subtracting, this overall limit approaches infinity, which means that our integral diverges. So because our integral from 2 to infinity of 1 over x to the 1/6 dx diverges, and we know that 1 over the square root of x to the 1/3 minus 1 is greater than or equal to 1 over x to the 1/6, then our original integral diverges as well. So hopefully on this worksheet you got some good practice in with evaluating improper integrals when we have infinite intervals, and evaluating improper integrals when the function that we're integrating is unbounded. And also, hopefully you learned a little bit about that comparison test. As always, if you have any questions, please feel free to let me know. And until the next video, good luck with your online learning.